Dr. Lindsay Fuller, formerly Staff Sergeant Lindsay Fuller, here at the Randolph Air Force Base JBSA Great Texas Airshow. And we are coming to you on Eclipse weekend, 2 days before the eclipse. We're working today, we're working tomorrow, and then we got an eclipse on Monday. We're going to be here all day, and we're going to have some fun.
Hi, I'm Lisa Shepard, and I'm here representing UTSA Physics and Astronomy at the Texas Airshow. We've got our swag here with information about the total eclipse coming up Monday. We have eclipse glasses that we are handing out. We've got other swag and a great demo showing the spectroscopy of different gases.
Howdy, Michael Preston here at the University of Texas San Antonio at the Texas Airshow. We are demonstrating a bunch of, giving information about eclipses out, but we're also doing a little bit of a spectroscopy demo. So let me show you a little bit what that looks like. We have these wonderful little diffraction grading cards. We'll put one of these over the camera so you can see what we're looking at. But what these do is they break up light. They break up light into all the colors of the rainbow. And we can use these to show how we do some of this space science and astrophysics. So, if I turn on this tungsten incandescent bulb and look at it through this little diffraction grating, we can see that it breaks up the white light of this bulb into all the colors of the rainbow. That's because this is a hot, solid filament. It's hot and dense, and it produces what we call a continuous spectrum. That continuous spectrum contains all the colors of the rainbow, and from continuous spectra we can determine things like temperature and, to a degree, the density of the material. Looking at this is kind of analogous to looking at the sun, which you shouldn't do through these. We have better alternatives. So, this is kind of an outdated form of light bulb, but we have a different kind of light bulb here that'll show us a little something different. This is a halogen bulb or a fluorescent bulb, and one of the reasons we switched to these is that they're a whole lot more energy efficient. You'll see I have to don protective gear to even touch this thing because it produces so much heat. A lot of that energy and the electricity is getting turned into heat. Ow. And this, I don't need the glove. This doesn't produce near as much heat, but still produces a bunch of light. Now, if we look at that through our little diffraction grating, you can see it nearly splits the light up into separate images of the halogen bulb. The reason for that is because it's not producing enough colors to make it look all smeared together. It's only producing a certain specific group of wavelengths that is specific to the gas that's inside of this bulb. I'll give you a little more in-depth explanation on what's going on there in a second. But one more kind of light we can look at, which I think is pretty cool, is the most modern type of light bulb, which is an LED, a light-emitting diode. We have an example here. This is an LED flashlight. Looking down here, you can see it produces white light, and through the diffraction grating, you'll see kind of all the colors of the rainbow, but specifically you should be able to pull out the blue, green, and red of the different diodes. Now you might notice that as I switch through these colors, you're only seeing blue, green, and red through the diffraction grating. That's because the LED is emitting only exactly one color. Now, returning to why this is more relevant to the science we do something called spectroscopy, where we use a version of a diffraction grating like this. It's a little more expensive, to look at things like the corona of the sun, for example, which you'll be able to see during the eclipse, weather permitting. And by looking at something like that, we're effectively looking at what's this halogen bulb. So this is basically a fancier version of the halogen bulb. This is called an emission tube. This is just a glass vial filled with hydrogen gas. And if I turn this on, you can see the hydrogen's emitting light as it's getting energized by the current, And through the diffraction grating, you should be able to see several different colors that the light is emitting. What you're looking at is the fingerprint of hydrogen gas. Those specific colors, those specific wavelengths correspond to the electron orbitals that are getting energized and then releasing energy at very specific wavelengths. And we can use that fingerprint to determine what different kinds of materials are present in different environments. So looking out into space, we see a lot of hydrogen, a lot of that pink color. It is the most abundant element in the universe. But if we look at, say, number 2, helium, we're going to see a slightly different spectrum. This is helium gas. If I turn it on, first you should be able to see that it's definitely a different color than hydrogen. But then if you look through the diffraction grating, you can also see different colors in different places and different numbers. That is a distinct fingerprint for this gas. Just like how hydrogen has its own fingerprint, helium has its own fingerprint, every element on the periodic table has its own fingerprint. Now, if we wanted to look at something a little more exciting, in my opinion, we would look at probably, I think it's a safe venture to say the most famous of the neon, the Nobel gases. I gave it away there. This is a vial of neon gas. I guess for the kiddos at home, you can guess what color this is going to be, because a lot of people get it wrong. But I think I like this one the best. We take a look at neon. You can see it's this brilliant, beautiful red-orange color. And if you look through the diffraction grating, you can see there's a lot of red, a lot of orange, some yellow and green, almost no blue or violet. So that's a short demonstration of how we can tell elements apart. One of the ways we can determine the composition of things like distant stars, planets, and clouds of gas in deep space where we can't go and, you know, touch, taste, feel it, smell it. So we're super excited for the eclipse that's going to be coming up on Monday, because we're going to get a lot of opportunities to do this kind of science on the inner corona, which you can only observe during an eclipse. So we're super excited here at UTSA and the Texas Hill Country and all across America. So make sure you have your proper eye protection, and clear skies and happy viewing. So that we don't have to go and take a sample, we can look and see if we see those same colors, and we can tell because of that fingerprint what material is actually in there. I can actually show you.
Right over there.
So it's got a violet neon.
What you give me no, I don't believe it. But it didn't help. We're looking at airplanes, but the only planes I'm seeing, I'm not gonna get into that.
Successful first day on the at the Joint Base San Antonio Airshow here at the Randolph Air Force Base. A lot of folks came through the STEM hangar. We had not as many planes in the sky or on the ground as we did the last time we were here, but we can thank the weather for that. It's cleared up now though, so the Thunderbird should be going on in a couple of minutes, and we're packing up. We talked to a lot of people. Handed out a lot of Eclipse glasses, and got a lot of mixed results talking to folks about the Eclipse. A lot of folks are going to be in the path, a lot of folks have a plan, a lot of folks got to work. I don't know who scheduled this thing on a Monday. But outside of that, super successful day. Here's to another one tomorrow.
Hello, my name is Finance Lorenzo Strickland IV, and I am with the UTSA Physics Astronomy Department. We are gearing up for day 2 at the air show here at the Randolph Air Force Base. Cloud cover is not looking too optimal. Clouds are pretty thick right now, but we still will be handing out brochures and eclipse glasses for the eclipse that's happening tomorrow. And we'll see if we can get people to come to UTSA, especially sign up for the Physics Astronomy Department program. So it should be a fun second day. Really just trying to hand out a ton of stuff we have left over and meet some people and have some good conversations.
This device is called a light sounds box, and what it does is it converts light into a sound here. And so we can shine light on this chip, and what it does is it produces a sound. And so we can demonstrate it here. We can turn this on, take a flashlight, and move the flashlight over the chip. And that way people who are blind or low vision can experience light in an auditory way.
So here we have punch cards, and with the punch cards, they're really fascinating because it's actually a way to indirectly view the sun. So if you have the sun behind you and it comes through these shapes we have here on the punch card, you can actually see the eclipse happen on the ground using the shadows. So what's really interesting is you have these shapes, but the shapes don't necessarily matter because the image that's projected through the shapes, you'll still get a circular image on the ground and you can actually see the eclipse. So this is like an old school way back in the day before glasses were really available to the general public. There was an indirect way of viewing the sun. So we're handing out punch cards here to the people here at the air show. here back at UTSA campus in front of the AET building where the Physics and Astronomy Department is located. We had a great air show. We handed out, I believe, around over 5,000 eclipse classes. So it went really well. We met a lot of people, handed out a lot of pamphlets on education for tomorrow for the eclipse. And it was a really fun event and looking forward to the next one. So if you ever get a chance, come by UTSA and check us out here at the Physics and Astronomy Department. Birds up.